Okay, thank you very much for the introduction, and very sorry for all these delays. So I was supposed to have 30 minutes, so I guess I have only 19 minutes left. So I try to speed up a bit so that we don't disturb the schedule. So my name is Sofian Tahar, and then this is a work conducted by my PhD student Mohammed Abdul Ghani, who joined a company locally here in Montreal, and could not basically make the presentation so late at night. It's now 10 p.m. in Montreal, just to let you know. And we are Tuesday, not Wednesday. So this is a work on the formal probabilistic risk assessment of a nuclear power plant. And that's an application using the HOL high order logic theorem prover. We are from the Department of Electrical and Computer Engineering of Concordia University in Montreal. So I'm going to start with an introduction to motivate this work, then talk about functional block diagrams, which are the modeling basically platform that we use to model and analyze the safety of a nuclear power plant. Then I conclude with a summary and some future work hints. So the central inquiry in many safety critical systems, as you know in this workshop, is really to try to assess the safety of systems using formal methods. And we are in particular interested in what we call risk assessment that can occur at the system or at the subsystem level. So for example, if we consider a smart grid, so it's composed of many subsystems, and then so we want to consider at the same time the system as a whole as subsystems, like parts of the grid. So in general, probabilistic risk assessment is a known methodology for planners and designers to evaluate the risk associated with safety critical systems. They usually go through a number of steps. First of all, they need to identify the risk. Then they need to conduct the risk and reliability analysis. After that, they have to come up with a risk response plan. And finally, so they have to implement some risk monitoring and control system. We are interested in this work about risk and reliability analysis. So we're not working on identification, nor a response plan, nor monitoring and control. All right, now the risk and reliability analysis can be characterized by two quantities. The first one is the severity of possible adverse consequences. And the second one is the likelihood of the occurrence of each of these consequences when an accident occurs. So this is basically the likelihood of consequences that are usually expressed as probabilities or frequencies, and that are determined through some reliability evaluation techniques. We distinguish here reliability modeling methods as well as reliability analysis methods. So there exist different modeling methods, for reliability, as many of you know. So for example, fault trees, reliability block diagrams, Markov chains, event trees, cause-consequence diagrams, or functional block diagrams, which are basically the main modeling method that I'm going to use in this work. So fault trees, as you know, they model the probabilities of a system failure only. So while RBDs, or reliability block diagrams, they model the probabilities of system success only. So basically here, so we start with a system, and then so we go through different paths, and then we actually find the failures. While with the RBDs, basically, so we have here the block diagrams that are either here in parallel or they are in series. And then, the success will depend on, for example, each of these to be successful in order to get an output with no failures. Markov chains are also very much known, and then they model the transitions between failures and working states. Now, event trees, which might be new to you, they model actually all possible risk consequences of system level, complete or partial failures, as well as reliability simultaneously. So basically, we start here with an initial node, and then actually a state could be a success, a failure, or a partial failure. So, and then so we can have branches, and then out of one branch, so we can have another node, and then so we can continue actually with further nodes and branching. And then each of these, so again, will carry multiple states that could be a success, a failure, or a partial failure. Now, functional block diagrams, they are built on top of event trees, and they allow multiple state analysis for each subsystem. Then at the subsystem level, event trees are composed together to make the functional block diagram. So for example, this is the functional block diagram system number 1, and this is system number 2. And then together, so they compose, if we flatten it, a huge event tree, but it allows us basically to reason at the block level. That's why they're called, functional block diagrams. So let me show you an example of a functional block diagram so that you understand the basically the modeling behind it and how it works. So this is an example of a steam turbine governor of a power plant. So it is composed actually of a power supply that we find here. There is an inductor motor, and there is here a steam valve. And then through that, so we have a steam flow basically that goes through this with a control here through like a monitor. Now, in order for the system to work properly, so we have to make sure that through the flow, so we have actually no failures. So if we now model each of these blocks with a functional block diagram, then for example, here we see the functional block diagram 1 of the power supply, which is in here. And then so with the command signals that are coming here from the computer, together so I supply the induction motor, which is here modeled as a second functional block diagram. Now, we have here the steam flow that is like flowing through, okay, the valve. And then the valve is controlled through the motor, okay, the induction motor. Then clearly here we can notice that if the computer fails or the power supply fails, then nothing is going to work. Or if these two actually are working, but the motor fails for whatever reason, then I cannot control the valve, right? And that's how the dependencies actually are taken care of. And this is all represented through this diagram here, which is the functional block diagram of the whole steam turbine governor, which is composed of subsystems. So we care about the reliability analysis of every subsystem in order to make sure that the whole system is working properly. Now, P1 to P4 are here like, properties that we want to check. And then for each of these properties, in order to be valid, so each of these subsystems has to work properly. All right, now how do we model this formally? Well, it boils down all to probabilities. So I was mentioning earlier that if this one fails, for example, the power supply, then if this one fails and so forth. So any system that you have, any component that you have in any system, you are given a specification, and in that specification, you are told that that particular component can fail by a probability of, for example, 0.0001%, or it's going to fail after 10 years or 20 years. So these are probability values that are usually provided, and in order to compute the probability of failure of the induction motor that is here, then this is depending on the power supply probability, okay? So this is probability of success, and then this is probability of complete failure, so CF. So we have here basically the probability of the power supply working successfully, then this is the control also successfully. But if we have a failure here of the motor, then we can have a failure of the whole system. Plus, we can add the probabilities of successfully working of the power supply multiplied by the probability for the failure of the computer, plus the probability of the failure of the power supply. And then so this is all together providing the probability of the complete failure of the induction motor. So similarly, we can reason about the whole system, right, as being the multiplication of all these probabilities to fail. Now, as a diagram, so you see them here described. So this is the first functional block diagram, the second one, the third one, and then all together, so they make the functional block diagram of this steam turbine governor, which when it is flattened, it's all composed of event trees. All right. Now, what do people use for the reliability analysis of event trees and eventually functional block diagrams? Well, paper and pencil methods, as well as some simulation tools, such as, Monte Carlo simulation. But we know, all of us, that paper and pencil can be very cumbersome. So this is just an example of a very small system. So imagine that the system has like hundreds of components. It will be very, very hard actually to just draw that and then, compute all the probabilities by hand. For the simulation, we know very well that we can only cover a subset of all the possibilities. And then so they're very much based on some random algorithms which are subject to failures. All right, so what do we want to do in this work? We want to use actually available reliability analysis methods for FBDs, and then we want to accurately compute the probability of risk. Now, we don't want to use simulation nor paper and pencil, but we want to use formal methods, to conduct that. So now this is recommended by several standards, like the one for electromechanical commission, or the European Community for Electrotechnical Standardization, or the International Standardization Organization. And this is actually what we are trying to do in this work. In particular, we want to do actually the probabilistic risk assessment of multi-level complex systems with multi-state components using theorem proving. And we want to apply it to a particular system, which is a nuclear power plant. All right, now how are we going to do that? So the nuclear power plant is modeled with the functional block diagrams, and we use higher order logic theorem proving, which is capable to reason about multiple level and multi-state of complex systems. So if we use, for example, model checking, or we want to use first order logic automated theorem provers, then we don't have these capabilities. In particular, we use the whole 4 theorem prover in order to conduct the probability analysis. Now let me talk quickly about this nuclear power plant that we are considering. So we know very well that nuclear power plants installations are very much vulnerable to accidents, which basically can cause the contamination with radioactive material. And this would make actually a large damage, to the surrounding inhabitants, or basically the environment as a whole. So there is a dire need to make sure that these are safe. And then we want to avoid radioactive disasters. Now, this is basically a diagram of the structure of the nuclear power plant. So first, we have here a nuclear reactor, which heats the reactor coolant, which can be water or gas. After that, so we have the reactor coolant that is passing through a steam generator, which heats water and produces steam flow that goes through here. And then after that, so we have some pressurized steam flow that goes through the steam turbine, which then starts to produce power. And then the remaining vapors actually is condensed through the condenser. So the condenser basically is used to exchange heat through a secondary side. For instance, we can have like, a river or a lake, okay, so that, this condensed water, can go through here, and then so it's cooled. But we can reverse the direction, and then we have the cooling water coming back, so that again we can use it for the steam generator, and the cycle will be repeated. All right, now we see here that this reactor is composed of several parts, and we are interested in particular for this boiling water reactor. And then so we have here several basically classes that we are considering. So we are starting here with some initial events, and these initial events basically could be a large loss of coolant accident, or a medium loss of coolant accident, or it could be basically a small, so here S, so a small loss of coolant accident, or it could be just a transient accident. Now, we identify different classes of accidents, right? Which we are here considering them one by one. So I'm going to talk about them, about each of these later on. Now, in high order logic, so I have here a predicate, basically, that is describing the functional block diagram. And then so it considers the different classes of accidents, that I'm here basically considering. And then so for each of them, so I want to make sure that they are successful. All right, now again, so this is the functional block diagram representing my reactor. So we have here the functional block diagram representing the reactivity control. And then the next one is the reactor coolant, as well as the inventory control. And the last one is for the decay heat removal. So again, each of these is represented as a predicate. And I use this particular operator, which takes basically the output of an event tree model, and then a partitioning of events. And then after that, so I can have reasoning about the reliability of these events. All right, now I take this one, which is basically the larger view. So each of these blocks now contains sub-blocks. So the first one, so is we have here the reactivity control. After that, we have the reactor coolant and the inventory control. And then finally, we have the decay heat removal. So if we look at this functional block diagram number 2, it's composed of two sub-blocks. One is for high pressure inventory control, and another one for the low pressure inventory control. And inside each of these blocks, we have, again, sub-blocks. So one is for pressure relief, and then so we have, other ones. So for example, here for coolant recirculation and so forth. Now, the beauty of functional block diagrams, as I mentioned earlier, is that we can have actually a hierarchy of blocks and then sub-blocks and then sub-blocks. So we have multiple levels, and then in every level, so we can have multiple states. So it's not just failure and success, but we can have failure, success, or complete success, or complete failure, or partial success and partial failure. And then this is all now combined together in one large predicate. This is the one you see on the left side. Probably is too small, to see, but this is how this is composed in high order logic. All right, now we have proved a number of theorems. So for example, this theorem number 1 is about the containment failing when the boiling reactor core melts. So and then this is described as
finish your talk in as soon as possible, because it's a kind of the time is set over. Sorry about this.
Okay, can I continue?
Yeah, sure.
Yeah. Okay, so I'm almost done. Okay. So here, basically, if we see about this theorem, so it's a multiplication of different probabilities, and then this is taken into consideration. So each of these here exponential to the power of minus delta here, and so forth. So each of these is representing one of these blocks, right? So this is the probability of failure of each of these subblocks that is provided by the vendors, basically from where we buy them, or they are basically making them. So this is another theorem, basically for the containment of intact at high internal pressure. And again, it is a multiplication of all these failure probabilities. All right, now we wanted to do some experimental analysis, and numerically we want to compare the results that we obtained through high order logic, or basically the whole four theorem prover, with a number of tools. So one is Isograph, and this is a tool for event trees. It's a commercial tool. Matlab, and then paper and pencil. So the paper and pencil analysis actually was conducted by a work prior to us, and that was the first work, that from where we got inspired. And we have here in this table the different outcome classes, and then basically the time for their computations using the manual. Sorry, not the time. These are the probabilities of failure and success. So for the manual approach, using Isograph, Matlab, and whole four. Then the last row here is about the CPU time, where we are doing it on the same computer. So the class number one is basically to check if the containment is intact when the nuclear reactor core melts at low pressure. The class number two is when the containment fails when the nuclear reactor core melts. Number three, the containment is intact when the nuclear reactor core melts at high internal pressure. And finally, the last one, the class number four, is when the containment fails prior to the nuclear reactor core melting due to some severe overpressure. So these are different scenarios of accidents. So we consider all of them with their probabilities. And then we notice here, for example, if we compare the manual approach to high order logic, we see that we have a better precision here. So we go actually so many numbers, after the dot. If we compare to Isograph, again, so we notice that we are not doing any rounding here, but we really have some exact values. So also, if we compare to Matlab, we see that Matlab is very far from this value. So basically, if you rely on Matlab, so you will get the probability of 0.019 instead of 0.013 as you would do it analytically or with a specialized tool. So as a conclusion, we see here that the values that we obtain through whole four are actually conforming with the values through the specialized tool, much better and more precise than the Matlab computations. So let me come to a conclusion. So in this work, I provided the formalization of functional block diagrams using the whole four theorem prover, which we used for the probabilistic risk assessment of large-scale event trees. And then we used functional block diagrams with different subsystem levels for the reliability analysis of the nuclear power plant. And then the verification of its safety classes expressions was successfully done using whole four. As a future work, we want to investigate dynamic failure and reliability events. So far we were considering these to be static, based on the probability multiplication of probabilities, but they could be dynamic, where the failures of the system are not happening at the same time, but they could happen at different points of time. So that would be basically one future work that we can consider. And for that, we need to use conditional probabilities that is available in the whole four theorem prover. So with this, I come to the end of my talk. So thank you very much for your attention, and I'll be glad to answer any questions. Thank you.
Thanks so much.